Hello. So this time we're going to go over the question of determining the projection of one vector onto another. And well, we have a clear geometrical interpretation of it, but now we have to make a transformation so that we can manipulate it algebraically. And well, but we're going to use the geometry itself to justify such formulation. So let me start like this. Note that from the picture that we can see, at least to get some intuition, note that U and V lie on a plane, and the angle alpha between U and V determines the direction of P. What do I mean by that? Well, if we have that alpha is between 0 and pi over 2, then P points in the direction of U. If we have that alpha is comprehended between pi over 2 and pi, then P points in the opposite direction of U. I'm leaving a third case, right? But let me explain it either way. If alpha is exactly pi over 2, then P is 0. Right? It's a 0 vector. The projection trivializes. Okay, so let's consider the first case. And I'll leave the second case really for as minor modifications on the following arguments. So I'll start like this for that justification. Let's see. Let's recall a few things. Recall that a vector is a quantity that possesses or that has magnitude and direction. Now, how do we identify these components of a vector algebraically? Well, imagine this. For a non-zero vector, x, we can write the following. The vector x is maybe decomposed in this fashion as the norm of x, the magnitude of x, times 1 over the magnitude of x times x itself. Now, let me put parentheses here to signify each of the elements, as this one that I'm underlining first is the magnitude, while this one, which is a unit vector, codifies the direction. Right? So we can do the same for this projection as we are considering this case. Right? So in the case where we have that alpha, the angle, is comprehended between 0 and pi over 2. So if you were to draw this on a diagram, the angle would be on the first quadrant in a coordinate plane. Right? Then P, the projection, can be decomposed as the magnitude of the projection times 1 over the magnitude of the projection times P. Of course, this one being the magnitude, and this one with a double underline, the unit vector in the direction of P. But in this case, both U and P share the same direction. So that means that the unit vector in the direction of U is the same as the unit vector in the direction of P. Now, making a substitution, we get the following. So look, we have managed to partially place P in terms of U. It seems like the only component that is missing now is describing the magnitude of P. Well, let's give it a shot. Also, note that P and V, as we can see from this picture that corresponds to this case, right, share the same angle. As U and V. But, well, let's go back to the picture itself, and then we can recognize that there is a right triangle involved, right? This one that I'm circling. Now, what are the sides of this right triangle? Well, if we make a reference to alpha, right, the angle here, the magnitude of P corresponds to the length of this side, while the magnitude of V corresponds to the hypotenuse of that right triangle. So we can write the following, or we can summarize that information using trigonometric functions. How so? Well, I can state the following. The cosine of alpha is nothing else but the ratio of the adjacent side, the magnitude of P, versus the one associated with the hypotenuse. From this, I can say that the magnitude of P is nothing else but the magnitude of V times the cosine of alpha. Now, there's one more thing. We're almost done. But for this one, I'm going to ask you to come up with some prior knowledge. There is a relation between the dot product of two vectors and the cosine. And what would be that relation? Well, it is this one. Also, the cosine of alpha, which is the same angle that U and V share, is the dot product U transpose V over the magnitude of U times the magnitude of V. Well, okay, so now it's just a matter of combining things. then we obtain that the magnitude of P is the magnitude of V times the cosine, but the cosine is U transpose V over the magnitude of U times the magnitude of V, which we can now simplify to the expression U transpose V over the magnitude of U. Well, let's put it all together. So, the vector P, which we described previously as the magnitude of P times 1 over the magnitude of U times U itself, well, now may be written as U transpose V over the magnitude of U times one over the magnitude of U times U. Of course, we can rewrite this in the following terms as U transpose V over the magnitude of U squared times U, using properties of the scalar product. But now, why don't we write everything in terms of matrix operations? Well, we can encode the following. We know that the square of the magnitude is nothing else but the dot product of a vector with itself. So in virtue of that, we can write this. And with this we finish. This is an algebraic formulation of the projection of U, of V onto U, well, expressed only in terms of U and V. And with this, we finish.